So this is the first lesson from Unit 9, Electricity. Notice that your essential questions are on the front of the packet for electricity. And in this lesson, I just want to cover 9.1, Electrical Potential Difference. So first, imagine with me that you have a charge placed at point B that's positive. We want to take that charge and move it to point A. Well, notice that we're moving it closer to this big positively charged particle. What we know about like charges is that they repel. Therefore, this charge, this positive charge, wants to get as far away as possible from this large positive charge. So by moving it from B to A, we actually are going to require energy, which is thus the same thing as work, as you remember from our energy unit. To move this particle, this positive particle, closer to another positive particle, we need to do work. This work, when we're talking about relating to charged particles, represents a change in the electrical potential energy. So think about the potential energies that you know, gravity, springs, giving something stored energy. That's what we're doing here, except it has to do with charges being positioned in certain places that give them energy. So we come to this thing called an electric potential difference, which is measured by the variable capital V. This measures the amount of energy that we absorb or release in moving a charge across a distance in an electric field. So imagine with me, and you've seen this similar thing before, we've got some positively charged plates and some negatively charged plates. You've got a nice electric field here between these two plates. And the beauty of the plates is they make our field nice and even, assuming they're the same distance across and they're perfectly parallel the whole time. Well, if I want to take a charge and move it between these two plates, I'm going to create an electrical potential difference. The energy we get when we move a charge from the positive plate to the negative plate here. But let's talk about that mathematically. First, if you take a look in your reference tables under the electricity section, you'll find V, and you'll see that it's labeled as electric potential difference, and that's related to the work done, W, over the charge that the work is being done on. So, if you want to take a look at units real quick, we know that work is measured in joules, and then charge we talk about in coulombs. So technically, electric potential difference could very well have the unit joules per coulomb, and that's totally fine if you want to leave it that way. But we also simplify joules per coulomb and get a unit called the volt, or we also represent it with capital V. Now, quick point here, don't get lost in this, but electric potential difference, the variable is represented by a capital V. However, the unit for electric potential difference is a volt. They're related, but one is the unit, volt, V, and the other is a variable, electric potential difference. So we can solve some examples with this, but first, just note, hey, areas of high voltage have high danger. Why? Well, because there's a lot of energy potential contained in those areas of high voltage. And therefore, if you have completed a circuit, if you let your body become a piece that's going to conduct that current, you can then be subject to a lot of that high energy, high voltage, which is dangerous. Okay, so let's take a look at two examples, just using this simple equation. If I've done 60 joules of work to move 5 coulombs of charge between 2 points in an electric field, what's the potential difference between these 2 points? So I've got 2 points, and I'm just moving a charge from one point to the other. I want to know the potential difference, so I'm looking for V. And I know V is a work over Q, so I'm going to put in my 60 joules of work over the charge. We've got 5 coulombs of charge. If you divide those out, you're going to end up with 12 joules per coulomb, which we also know is 12 volts. And again, if you did the same thing, we've got the potential difference of 10 volts, and that exists between 2 points, A and B, where within an electric field, what's the magnitude of the charge we're looking for that requires this much work to move from A to B? So again, I'm moving the point. I've got my equation, V equals work over Q, and I'm going to substitute in what I've got 10 volts. I know the work's 2.0 times 10 to the negative 2 joules, and I'm looking for the Q. you want to do a little cross multiplication, that's not going to solve for this. Multiply each side. You end up getting 10 V times Q equals 2.0 times 10 to the negative 2 joules. And if you put this in your calculator, you get Q equals 2 times 10 to the negative 3 coulombs. But often, small amounts of work or energy are represented by a different unit. So we have really small amounts of energy. We get rid of the coulomb and we talk about something called electron volts, which is the amount of work done moving on an elementary charge. In other words, an electron or a proton through a potential difference of 1 volt. So if you think about this, your elementary charge, which is your electron or your proton, and this is the process of charges moving from one plate to another. So where we have the charge of 1 electron, if you have 1 electron, you have 1.6 times 10 to the negative 19 coulombs. Well, here, this is just talking about our electron and the charge on a single electron in a single volt. So, for example, if a proton is moved through a potential difference of 10 volts in an electric field, how much work, this time I'm looking in electron volts instead of joules, this is our smaller unit, was required to move this proton. So I'm going to set it up the same way. We've got V equals work over Q. Now I'm looking for work. I know the voltage is 10 volts. And I'm looking for work. My Q, since I have a single proton, is just 1 elementary charge, or 1e. It's positive since I'm a proton, could be negative if I was an electron. Now, if I solve this and multiply 1e times 10, and I'm going to get 10 electron volts as my work unit. Now, notice we're not using coulombs in this point. That would have given us joules. We're using electron volts, which uses our elementary charge, just 1 electron or 1 proton. So I want you to take a look at these parallel plates, and I kind of drew a similar picture to this before, but between a pair of charged parallel plates, what you can know is that you have a constant electric field, and that you can show by the closeness of these lines here. If both these plates are perfectly parallel, these lines are perfectly spaced out, and we can assume that these plates go on for infinity, giving us a completely constant electric field between one plate and another, assuming the distance is the same the whole way throughout. The electric potential difference then depends on the electric field and on the charge between the plates. As we change those two things, we can change the electric potential of taking a positive charge and moving it. So mathematically, we can think of this very similarly. Let's start with V equals work over Q, except I'm looking here for the electric field, which we know is E. Well, let's make a quick substitution here. We know that work is the same thing as a force times a distance, and we still got it over Q. Now, in this case, the force that would be doing the work is the force, the electrostatic force, so I'm going to substitute in an E there. And then I can see a nice conclusion here. Fe over Q. Oh, if I take a look at our previous unit, and in that reference table, Fe over Q is the same thing as E, the electric field, and I've still got distance in there. So I come up with that. Or I can see that if I want to solve for electric potential difference in terms of the electric field, I can simply do the electric field between two plates multiplied by the distance between those two plates. And I'll be able to arrive at my electric potential within those two plates.